circuit more linear up to a certain point. So we saw that in this case, actually, if you look at it, the gain of this stage, we saw that, well, this current, this collector current and this emitter current are pretty much the same, except for a factor of alpha, right? So I need an alpha. And what controls this really the emitter current is this voltage, right? If you think about the T model, there's an Rn here and there's Re, right? Alpha Rn and Re. So it's really the same current being carried through both of these branches, the upper branch and lower branch. So the variation in this voltage and that voltage are related to that current, right? So it's really the gain is nothing but, with a minus sign, the total resistance or the total impedance in the collector divided by the total impedance in the emitter. In this case, the total resistance is RC and the total resistance in the emitter is RE plus RL. So you can see that even by looking at the circuit, probably you should be able to tell what its gain is from this perspective. From an AC perspective, if you have something like that, say, well, if I show you something that's about 5K here and 1K here, now you know that, well, it should be approximately about 5, probably a little less than 5 because they have an Rm here. Right? If I show you 50 ohm and 10 ohms, what would you tell me? Well, of course, I have to tell you what the current is, right? So let's say it's 1 milliamp. So your Rm is about 25 volts, 25 ohms, right? So then it's not 5 anymore. It's 50 divided by 35, so it's less than 2, right? But you can tell it's the total impedance here divided by the total impedance there. The other thing that we noticed is that from an impedance perspective, whenever you look into the base, because this current, the base current, is beta times smaller than that. Whatever you have in the emitter gets multiplied by beta plus 1, right? So this current, the emitter current, is beta plus 1 times the base current. And therefore, from the impedance perspective, this impedance, whatever impedance you have in the emitter, will be multiplied by that. So in that case, you get 1 plus beta times alpha Rm plus Re. Now, 1 plus beta times alpha Rm is exactly our pi, and this is 1 plus beta Re. And this was what we call the reflection rule. You can also do the opposite. You can take an impedance from the base, if you have resistance here, and divide it by 1 plus beta, and move it to the emitter. Ballpark, beta. Multiplied by beta, divided by beta. And for all practical purposes, it doesn't matter. The 1 doesn't matter. The beta is such an inaccurate parameter. Anyway. So, for all practical purposes, this times beta here, this divided by beta there. And that was a useful thing in determining the input and output resistance of this thing. Because if I take my output out of here, I could have asked you to calculate my output resistance, right? So let's do that now. I didn't ask you this, but let's do it. So if I ask you, what is my output resistance? What would you tell me? Well, if I didn't have an RO, it's simple, it's just RC, right? But let's say you do have an RO. So let's say you have some output resistance is RO. So what is that? What is the output resistance now? Well, you have to know what is the output resistance of this degenerate transistor, right? And we have calculated that. What is that output resistance? Does anyone remember?
B of the IC. B of the IC.
Well, that's RO. But that's the RO itself. But now that I have an resistance in the emitter, what is the total?
Additional resistance.
If the source resistance is 0, AC. AC is ground. Well, we did the calculation. It was
R0 into
RO times 1 plus GM RE divided by alpha Re, but it doesn't matter. 1 plus GM RE over beta. And that was the reason that when we increased RE, even if you made it infinite, this became the maximum limit of this guy was beta RO, not infinity. You couldn't go beyond that. So that's a good thing to remember. And then of course that's in parallel with RC. So that's from this perspective. But now I could take an output from this node as well. Does it mean that it has the same output resistance? Not at all. The output resistance is a function of where I'm looking at things. So if I were to look at this output resistance, what would you say my output resistance is? Let's say I have no base resistance, so basically this is short. AC short. It's an ideal voltage source.
RE in parallel to RF?
Yeah, exactly. Right? This node is short. So think about the T model. You draw the T model, this is alpha Rm here, it's shorted here, this is the Re. I'm looking at this. So you should be able to determine those things now by looking at them. And the same way, so basically, if you look at it really from here to there, it's just a follower. If you look at it from here to there, it's an amplifier. I mean, it's a common emitter with differential generation. And we also have the common base. We have the common base where we basically applied the input here and took the output there, and we saw that it's not fundamentally similar in what we're doing to the common emitter, right, this guy. Except for the fact, in this case, I kept this terminal on the reference and moved this one. Now I'm keeping this terminal on the reference and moving this one. Now, from a gain perspective, that results in the same game except for the change in polarity, because I'm changing the polarity of the input, right? It's like switching the two terminals of the input. So the gain of this thing would be GM-RC, right? However, the input impedance is different because now from the reflection perspective, if you think about it, I'm looking into the emitter. So I basically see alpha or N. If you want to think about it, the input impedance on this guy was R pi, right? So I have to divide it by 1 plus beta, which gives me exactly alpha or N. Or, even yet simpler way of saying that is that you look at the T model, you have an alpha or N in the emitter. So, and then we saw that one interesting thing about this stage was that the intrinsic part of the output resistance was what? Well, let's say I have some source resistance RS. The intrinsic part is the part looking down, other than RC. So what is that? What is that output impedance? Looking down. It looks exactly the same as that, right? For the purpose of the output impedance, because this node is grounded and this node is grounded. So is this one and that one. So it's exactly the same thing. So now its output impedance is also similar to that, but now if I drive one with a highest impedance source, namely a transistor, a common emitter, I can form the cascode. And now if I have to look it down here, my RE or RS looking down here is simply RO. Therefore, I have to plug RO into this equation, and see, I have GMRO and GMRO over beta. And both these quantities can be quite large, and therefore, what I get is effectively beta RO. Yeah. And that's why it has a higher intrinsic gain than that of the common emitter, Cascode. Right? Cascode gives you an intrinsic gain beta RO GM. In other words, beta VA over VT. Beta times greater than that of the common emitter. And I could play the same trick on the MOSFET side. And in fact, on the MOSFET side, I was in a better situation because I didn't have this beta limitation. Beta is infinite for a standard MOSFET 3. One way to think about it. So that was one of the basis of one of the techniques that we used extensively to increase our gain in stages, right? So we said, well, if we want to get a high gain stage, what I need is to basically make this and also make a load that's a high impedance. So the first load that was high impedance was a transistor itself, used as a current source. And we saw that gives you output impedance of RO. But then we saw we could go actually beyond that by introducing a cascode current source. So one of the things that we could make, for instance, was something like this. So you can have a cascode stage, so this would be in, EB1. So this is a driving stage, and then it can go to a load that can be formed by a cascode of PFETs, PMPs, I'm sorry. I'm taking the output from here. And now, if you look at the drive, so there are two components that result in the gate, right? There are two things necessary for gate. The drive and an impedance, right? So the drive here is, if this voltage is VN, right? This current is GM-VN. Right. And now you say, well, wait a second. Why do you say all of this current goes into this guy? Right? Because there's an RO here, too, right? But you have a current divider, right? Between RO and what? What do you see looking up? Rm. So RO is, the ratio of RO to Rm is the ratio of VA to VT. It's huge. So this is a much lower impedance than that impedance. So pretty much for all practical purposes, all the current goes into the emitter. Now, what percentage comes out? What is this current? Almost the same. It's alpha GM pulled out of that node. Now, what is the impedance on that node? Obviously, we've calculated this. Looking up, what do I see? If I just do it this way, beta ROP, and I see beta PROP, and then looking down, I see beta NRON, and of course, the parallel combination of that times alpha GM. That gives you the total gain. And now, we did that in a differential form as well. So, one of the things that we then did was we looked at differential amplifiers. We saw that one way to make it, the idea of differential amplifier is to make an amplifier whose output does not change when both inputs move in the same way, in phase, the common mode, right? So the idea is that if I make two common emitter amplifiers, right, like this, independent of each other, I can apply differential input to this and I will get a differential output at the output, right? If I just apply its differential input, I get a differential output. The problem is that if there's a common mode to these two parts, that part gets amplified and shifts the output too. So if I just shift it up by a certain amount, both of them, the output will drop. Both outputs will drop. And that's not a good thing. But I wanted to get rid of my common mode because that's where a lot of my noise and pickup came from. So I wanted to get rid of it. So the idea was to somehow maintain the total current constant. If I keep both currents constant, and if there's only a symmetrical voltage applied, basically, which is the same on both sides, because of the symmetry, no one side can draw more current. So therefore, both currents have to remain, the sum of the individual currents, the sum is constant, they are equal, so they have to remain constant. Right? So how do I keep these two currents, the sum of these two currents constant? I bias them with a current source. If I bias them with a current source, what happens is that the sum of these two currents have to be the same. And if I apply symmetric input, which is a common mode signal, then they have to be the same. They have to be equal to each other, and therefore they can't change. So in this case, if I apply common mode voltage, what happens is that this node follows that node, but these guys will not move at all. Of course, up to a certain point, until the transistor enters saturation. If I just raise it so much, the transistor can go into saturation. But for as long as I remain in the forward active region, for the simplified model, if I don't worry about the RO and the output resistance of this guy, it doesn't happen. It doesn't move at all. But practically, of course, I have some resistance associated with this, and I have some output resistance here, but nonetheless, it still works quite well. So now, in a differential amplifier, we wanted to get more gain. One way to get more gain was to improve the load, and we saw you could do that by using an active load like this. So you could use PMPs like that, and use these two current sources as a load, and you get a differential output. And the gain, of course, is GM ROP compared with RON. Now, one question that was raised at that point is that how do you make these current sources? How do you bias these guys? And we saw that you could actually make these reference branches like that. It could be biased by some reference current. And here, this could be a basic transistor that could be biased with another branch using a current mirror. We saw that in a current mirror, these two VDEs were equal. So the first order, these two currents have to be the same. Of course, there was the base current to be accounted for and the early voltage, the early effect. So, one thing that we did, in this case, he said, well, we assume that we have a reference branch, and if you had a reference branch, you could actually replicate it many times using this current mirror right here, like this one, where you could replicate it twice, and could replicate it more often, and I could actually get different ratios by adjusting the ratio of these guys, or I could make it smaller by putting a resistor here, like a wider current source, or I could even make the current mirrors Cascode, and you look at all of those. Now, one of the things that was we talked about how to generate these references, right? We saw that there were different kinds of cores, the temperature-independent and supply-independent core. So one of the things, for instance, we did was make a VBE core, right? A core that generated the voltage that was proportional to VBE. And we saw that for that, one of the things we could do was to make these so-called floating mirrors that force these two voltages to be equal and the two currents to be equal. So something like that. And then we drop that voltage across the resistor. So this voltage would have been the VBE, would be the VBE of this guy, and therefore this current is basically VBE over R, and then you can replicate, you can copy this current somewhere else and use it as your reference. So this whole thing would be your reference, VBE reference. But the problem with the VBE reference, for instance, was that VBE had a negative temperature coefficient, and resistors, typical resistors, positive temperature coefficient, so this thing is not very independent of temperature. So the next thing we did, we said, well, how can we make a VT reference? Something that's proportional to KT over Q. And we saw for that, we have to get rid of the IS. The way we got rid of IS was basically by, instead of dropping the VBE across a resistor, dropping the difference of two different VBEs across a resistor. And the way we did that is that we'll say, if I make this voltage another VBE, so if this is VBE1 and if this voltage is VBE2, then the voltage across this guy is a difference of two VBEs. And the way I achieved that was by putting another transistor here and put it across a resistor. Of course, these two transistors cannot have the same size because this VBE has to be smaller than that VBE. Otherwise, this voltage would be zero, right? So the way we achieve this is by making this larger transistor. So for a given current, it will have a smaller VBE. Let's say n times larger. And if that happens to be the case, then the current coming out of here, we saw it was basically VT natural log of n divided by R. And this VT was proportional to temperature. Now the last thing we did was that we saw that the VBE itself had a component proportional to VT. And if we add the but in the opposite side, so we said, well, if we add this VT, let's say this is another R1 is R2, to the VBE, we could actually extract the voltage that was proportional to the band gap, if you make this the right ratio. So we generated a voltage that was proportional to the band gap of the semiconductor itself. And hence it was very independent of temperature and didn't change with process variations as much and did not change the supply at all. And therefore we could use that as a voltage reference, or we could use these currents for current references. And then we put all of this stuff together to make an op-amp, right? We used these different stages that we had and put them together. We saw that you needed, in the bipolar case, you needed to get the higher gain, you needed to increase the output impedance of that node, maintaining the drive constant, and therefore basically getting higher gain, but you needed to add additional buffer stages to make sure that you are not loading those high impedance nodes. And we saw to get the voltage gain, you need a high impedance node, right? So there are two ways to increase the voltage gain in general: the drive and the impedance. You either have to burn a heck of a lot of current to increase the GN and keep the impedance low. That's what you do if you want to make very fast circuits, right? Because if you want to make a fast circuit, you don't want a high impedance node. Unless you don't want a high impedance node that has a reasonable capacitance. So there's a third element to this. So if you can somehow reduce the capacitance of a high impedance node, it's okay, but that's usually a difficult thing to do. So what remains is to either reduce the impedance and burn a lot of current, which basically gives rise to the basic trade-off between speed and power consumption. Or, if you want to get the gain, you have to bite the bullet and say, well, okay, I'm going to tolerate a smaller amount of gain, a slower speed, and increase my impedance if I want to maintain my current consumptions. And then we saw all those trade-offs in different examples. We looked at different op-amps and some numerical examples. We did some, and you verified some of this with SPICE, looking at your simulations. You saw that you can actually look at these, and we'll do quite a lot of that next quarter. So next quarter we'll do more SPICE, and what we'll do next quarter, so let me just quickly tell you what TE1 for TE is all about. What we'll start with, we will go over this capacitive components of elements, transistors, and BJTs and MOSFET. And then we start writing, we look at general behavior of systems in terms of frequency response. We look at poles and zeros, what poles and zeros mean really in a system, what kinds of poles and zeros we can have, what gives rise to poles and zeros, and then we relate them to circuit parameters. The dynamics of the circuit. We look at the Bode plot, the root locus of the different circuits when we apply feedback. And then, so we determine the frequency response of these individual stages first. So we start with common emitter, common base, common collector, and the equivalents for the MOSFET. We look at those, we analyze them very carefully, we understand how they behave from frequency domain perspective. And then we start putting them together. And we do several design examples. We say, well, if you want to make something that's this fast and it burns this much power, how we do it. And then we go through the evolution of the design for that. And then we come back and we talk about some other effects. So we talk about noise, which is one of the parameters limiting the lower end of signal levels. See, the signal levels in electrical circuits are limited from both sides. On the upper end, it's the nonlinearity of the circuit, right? You don't want to clip the signal. You don't want to distort it too much, right? And on the lower end, it's the noise. So we'll talk about the physical mechanisms giving rise to noise. Talk about what causes noise, what different kinds of mechanisms are there. How we actually model the noise in electrical components like transistors and diodes and things like that sort. Where they come from, how we model them, and then we go and analyze the noise in different circuits. We look at their noise performances of different kinds of topologies. Then we put them together, and that's why we need to do the frequency response first, because we look at the frequencies, noise behavior in the frequency domain, and not just at one frequency. And basically we take it there, and the next step is we look at feedback in circuits. We look at frequency compensation. What happens when you apply feedback? The circuit in general can be unstable. We look at that, and we look at how we can stabilize circuits like the op-amp that has been designed. And we see exactly why we need as few stages as possible, what happens to poles and zeros, how to compensate these things, and we go and then at the end, actually at the end of the class, depending on what you like and all those things, I can talk about different topics. Usually I talk a little bit about A2Ds or PLLs and all those things, different topologies. You go a little bit higher level, system level, see how we can make it an A2D. Let's say you can make amplifiers, you can make with we talk about comparators, high bandwidth amplifiers, how we design those, and say, well, let's say you can make good comparators and good amplifiers. What are different ways of making A2Ds or D2As? Or if you want, you can talk about some other topics like filters or PLLs or other topics. So that's what we're going to do next quarter. So that's basically where we're going to be. And I don't want to keep you away from the pizza for too long. So any questions on this stuff? I mean, I tried to kind of quickly review the top level of what we went over and what we'll be going to talk about this quarter. Any specific questions about stuff we talked about so far? No? Okay, yes.
How do you determine, like, if you're given a circuit, how do you determine which transistor goes into saturation, how much is the maximum voltage?
Okay, well, you see, one way to deal with that, I mean, that works most of the time, is that you can start with the circuit from a large signal perspective, assuming that the transistor is in forward active region. And then go and look at determine for one, I mean, don't do the whole thing, just look at the stage in question, the transistor in question, and try to determine with that assumption what the DC levels are, right, the current, and come back and see if it's consistent. Let me give you an example. Let's say if we take this one and I say to you that, you know, this is the 100 kilo ohm resistor and this is a 1 kilo ohm resistor, and I set this DC level voltage to let's say 1.7 volts, DC wise, somehow. I mean, I'm oversimplifying. So, what is this transistor? What mode of operation? So let's say I assume that it's in forward active region, and say, well, okay, well, this is a VBE drop anyway. So this is about whether or not it's in forward active region. As long as this voltage is higher than that voltage, it's about 0.7, 0.8 volts. Right. So this voltage is about 1 volt, and I have to tell you what this is applied. Let's say it's 5 volts. Right. So if this is 1 volt, 1K, this is about 1 milliamp, right? So, but what is this voltage? If that's 1 milliamp.
We calculate the predicted current from that.
Right, so it's 1 milliamp. What is this voltage?
5 minus 100.
5 minus 100, right? Minus 95 volts. Right? So it is now. So before that happens, so if let's say for the sake of argument, it is minus 95 volts, and this voltage is 1.7 volts. What is the voltage on this junction? First of all, is it reverse biased or forward biased?
0.2.
No, this between base and the collector.
0.4. Saturated, right?
No. Let's just, for the sake of argument, assume that this voltage is 95, no, minus 95 volts. So the voltage across here is something like 96.7 volts, right? Forward biased. That's one unhappy junction, right?
So it is saturation down for this.
Yeah, of course. So that tells you that there's something wrong. So this junction has been forward biased a long time before that. So I go back and say, well, okay, so let's see what the actual voltages are. So then it means that this voltage, this cannot go below 0.1 or 0.2, right? Because once this gets forward biased, this will be 0.6 volts forward. So that means something like 0.1, 0.2. So if this is 1 volt, this will be 0.2 volts above that. So this is 1.2 volts. That's 5 volts. And let's see what I get now. Right. So what is this current?
5 minutes, so it's 300 by 100K, so
So it's 3.8 divided by 100K. So it's, let's say 0.38 divided by 1 mega ohm. So that's, is it correct? No, nice one.
Sorry.
Yeah, 38 divided by 1 mega ohm. So that would be 38 microamps. Right? And this current, what is this current? This is 1 volt, this is 1K.
it's still the same.
1 milliamp. This is 38 microamps. So, is this consistent? Is this correct?
No.
Yes, no?
Yes.
Yeah, it is consistent because this junction is forward biased now. This is carrying a lot of current through here that goes back in here. So that is correct. I mean, this will be carrying, because your base current is now huge. You have a reasonably large base current because it's forward biased. There is no, and in that situation, there is no guarantee. If I forward bias this junction, there is no guarantee that this current will be alpha times that current. Most of the current is flowing through here, there will be a leakage current flowing through the collector. And that's what it is.
So if we have like multiple stages that the emitter of this connected to the base of another one, and that.
Oh yeah, it can mess that up too. I mean, let's say there's something before us, is that the question? So let's say there's something driving this.
Yeah.
Right? If this one goes into saturation, it can draw a whole lot of current from there and it can mess that one up too. It doesn't happen in MOSFETs because there's no base current, but in bipolars that can happen also.
How do we decide how many, like, if he gives us a big circuit, then how do we decide how many transistors do we have to consider for, like this is being driven by something else, that is being driven by something else?
Well, the thing is that once, if let's say this were not in saturation, right? You determine this voltage and look back at the transistor, see if it's consistent with its point of operation. If it is, you're okay. If it's not, then you have to say, well, if this is saturated, then what happens if it's not? And then you have to keep going till it becomes consistent, right? Now, how do you know it's going to go into saturation up front? And you asked me about saturation, I put down the circuit, and I knew it's going to go to saturation when I put it down on the whiteboard. How did I do that? It's very simple. This is a good thing to know, I mean, to articulate. You probably already know it, but you haven't articulated it properly. No, this voltage and that resistor. And the current now, right? Exactly. So I said, I was thinking, okay, I'm going to make this 1 milliamp. That's my favorite current because I know all the numbers for that. And of course, if I need something else, I can scale it from 1 milliamp. If I need 100 microamp, I can divide it by 10. But, right? So I said, well, I made this 1K. I said, well, I make this 1.7 volts, so I knew that this is going to make it 1 milliamp, right? And I said, well, if I pick a large enough resistor here, I will saturate the transistor. Right?
So what exactly is large?
Large enough resistor for a given voltage. Large enough is this. If this resistor divided by this voltage divided by this resistor, right, doesn't give me enough current, it means that this is not capable of handling that current. So let's say the lowest this could be in the circuit is ground, right? If I connect a 100 kilo ohm here, between 5 volts in ground, what is the current in that? 50 microamps. Right? So the maximum current this guy can handle is 50 microamps. So if I try to pull anything more than that, or even that, I would drive it into saturation. Now, in this case, actually, I can't even draw that because what happens is I need a volt here. So I'm losing a volt here. So I'm losing 0.2 here, 0.1. So I actually, if I want to see where it goes in saturation, I have to think about it this way. This is 1.2 volts approximately. And what that current is, that's kind of the minimum current. The maximum current I can have before going to saturation. Now, another way of avoiding saturation would have been this. Right? That wouldn't go into saturation. So, the combination of this supply and this resistor were not capable of carrying current. If you want to even get deeper into it, another way of thinking about it, think about the Norton equivalent of the circuit. This is the Thevenin equivalent, right? The Norton equivalent, what is the Norton equivalent? So the Thevenin circuit looks like this, right? If I draw the Thevenin circuit, this looks like 5 volts, 100 kilo ohm, right? The Norton equivalent of that 100 kilo ohm is the same, right? The current will be that 550 micron. That's what I was doing really. So the maximum current this guy can give is 50 microns. If that's not enough, then something has to give.
So the 0.7 came from the fact that like threshold would be 0.7. The 0.2 is
Now, so I would call it threshold, right? That's not confusing.
so and the 0.2 comes from the connector.
Well, 0.2 is basically, I said, well, for this junction to start carrying any reasonable voltage, it has to be at least 0.5 or 0.6 volts forward biased, right? If this is 0.5 or 0.6 and this is 0.7, so this is 0.7 above and then 0.5 below. So it's 0.7 minus 0.5, it's 0.2 or 0.5. That's actually a better way of thinking about it. If you want to, instead of 0.1 or 0.2 volts, say, well, when this junction is forward biased by 0.5 or 0.6. Because that will force you to think about this junction as a forward biased diode. As opposed to thinking that there's a little thing there, 0.1, 0.2. It's a forward biased diode. So whatever, if you have, see, in that case, the way to analyze the circuit is simple. In that case, because I'm not worried about that stuff, that circuit is behaving exactly like this. So this is one circuit where my two diode replacement of the transistor does exactly the same thing as the transistor. Because the transistor is not really transisting anymore, because that's gone, that behavior. Both the collector and emitter are pouring a lot of electrons into space. They're dumping electrons. And that's why that once the transistor goes into bipolar transistor goes into saturation, it takes a heck of a lot of time for it to come out of saturation. It's extremely difficult. It takes a while for it to turn off. Because you've dumped a lot of charge into the base. So if you remove everything, the charge will still, well, I'm here, I have to go somewhere. Right? So it carries more current. Yes?
In the forward active case, there are two diodes. Doesn't there need to be a DC path from the emitter to the collector also? How does that?
Yeah, see that's the thing. So actually you're right. So this is not exact. So I still need that current source. See, the forward bias is provided by that alpha R current source. See, this guy. You're right. You're right. Even in that case, you need that. So take it back. Even in that case, my two diodes equivalent. I can't even get that to work for something. You're right. So even in that